Let's now look at the Poisson probability distribution. A Poisson random variable is a number that occurs over a specified interval of time or space. And the thing to note here is that it could go all the way up to infinity. So, more concretely, let's consider some examples. So the number of knot holes in 14 feet of a wooden board, or the number of vehicles arriving at a toll booth in 1 hour. So for instance, the number of vehicles could be 0, or it could be all the way up to 50,313. Bell Labs was the first to intensely study the Poisson distribution to model the arrival of phone calls, because in the old days, telephone operators received a number of calls per hour, and they would use that study to determine how many telephone operators to field. Here are the two main properties of the Poisson probability distribution. Please take note of the second. The occurrence or non-occurrence is independent of the other events. And now note the first, that the probability of an occurrence is the same for any two intervals of equal length. So let's have a look at that. This is the equation of the probability distribution for the Poisson. So what we will be interested in is x, the number of occurrences. And all we need to do is we need to know mu, the mean number of occurrences, and e is just an exponential constant. So if we know mu and x, we just plug them into this equation, and we will get the probability of x being 0, or 1, or 17. And be careful, since there is no stated upper limit, the maximum is potentially infinite. Although in practice, x will become large enough so that if x is really large, then its probability is close to 0. So for instance, the probability that there will be 1 million cars showing up at the toll booth is pretty much 0. Consider the case of Mercy Hospital. On average, 6 patients arrive per hour. So this is mu. We are now interested in finding out what is the probability that there will be 4 arrivals in 30 minutes. Please think a minute of how you would use the equation to solve this. Remember, mu equals 6 per hour. Hence, there must be 3 for every half hour, and hence, that is the value that we should use in the equation. And remember, we are interested in the probability that there will be 4 arrivals, hence x equals 4. So plug in the values 3 and 4 into the equation, and you get 0.168, which means that there is a 16.8% probability that there will be 4 arrivals in 30 minutes. And now please try for yourself and calculate the probabilities that there will be 1 arrival, 7 arrivals, or also try 0 arrivals. This is how the distribution of the probabilities of the outcomes would show up. As you can see, for large numbers of arrivals, the probability is pretty close to 0. As with the binomial distribution, several properties have been established by statisticians. So the nice thing is that the mean and the variance of the Poisson probability distribution are equal. Hence, if we know the mean, which was 3 for 30 minutes, then we know that the variance will also be 3. At this point, we're just going to skim through the hypergeometric probability distribution. Please go through the slides, but as I note at the end, the hypergeometric probability distribution devolves into the binomial probability distribution when the population size is large. Hence, in this course, we won't pay much attention to the hypergeometric distribution.